Okay, so for our two-way mixed ANOVA example, here is, let me put my laser pointer on again. This is our sample data set. And I actually think the student version of the layered statistic example that I gave you guys also has this. So you'll be able to take a peek at that if you're interested in it. But the purpose is a researcher was interested in discovering whether the intensity of an exercise training program had an effect on cholesterol concentration over a 6-month period. So similar to previous weeks, I've highlighted our independent variable in yellow and our dependent variable in green. We have 45 sedentary participants randomly sampled and equally divided into 3 groups. So that's already hinting that the grouping we're using is our between subject variable. One group, in one group, participants did not change their current sedentary lifestyle. So if we're looking at the separation of the intensity of an exercise training program, we have a sedentary group as one level. In another group, participants underwent a low intensity exercise training program that expended 1,000 kilocalories per week. So that's our second level. And then the third group underwent a high intensity exercise training program that also expended 1,000 kilocalories per week, but therefore they exercised for a less total amount of time just because they're working harder or at a higher intensity. So that would be our third level for our intensities. All interventions lasted for 6 months, and cholesterol concentration, which is our dependent variable, was measured prior to the intervention, midway, and at the end of the intervention. So if we kind of split all of this up, we have our between subject independent variable, which is exercise intensity, where we had a control group, which was who stayed sedentary. We had a low intensity group, which will be abbreviated as INT1 in the rest of our output examples. And then the high intensity group, which will be labeled as INT2. Okay, so 3 levels of our exercise intensities. And then the time at which we took our measurements was pre-intervention, which is our baseline measurement, mid-intervention at 3 months, and then our post-intervention measurement at 6 months. So again, another within subject variable, we've got 3 levels. So when we name this, and I'll actually have you guys practice naming your ANOVAs this week. We've got either, we could say it's a 2-way, or if we're using a level by level naming convention, we would say it's a 3x3. And then as far as the type of samples, our descriptors could either be mixed or between within. So the order of the levels should match the order of between within if you're using a level by level naming convention. So let's say that instead of looking at the sedentary control group, we ended up just having a low intensity and a high intensity group, which would just mean we have 2 levels of the between subject variable, but we still keep 3 measurements for everybody. So that would end up being a 2x3 between within. The 2 levels would indicate the between subject factor. The 3 levels would indicate the within subject factor. So the order in these ones do matter. Since this one has both 3 and 3, obviously it doesn't matter what order you put the 3s in because each one is describing between and within. But our 3-way between within this example here, that'll be the naming convention that you guys use on your activities and the discussion this week. So whenever I say like level by level naming convention, that's what I'm referring to as like this last one here. Okay, so setup wise, I've separated the variable view for the between and within subject factors because the way that they go into SPSS, if you are drawing from our previous examples that we've had for independent ANOVAs and repeated measures ANOVAs, we're just like slapping the two together. So when we had independent ANOVAs, we needed to have a measure that was associated with certain values that were associated with the levels of our between subject variable. And then we inserted that as a nominal measure. So for the between subject variable, usually it's going to be listed as the first variable. When we go into the data view, it would be the first column. Okay, so keep that that kind of organization consistent throughout all of the between within examples. It honestly ends up helping quite a lot. But for this one, our exercise intensities have been labeled as group. So that's the variable name. And then we list it as nominal because we have certain values that represent our different groups. So in this example, 0 was assigned to our control or sedentary group. 1 was assigned to our low intensity exercise group, and then 2 was given to the high intensity exercise group. So you guys will set those up in the examples you have to work with this week. For the within subject variable, you'll recall from last week, for each level of the within subject variable or variables, there is a corresponding column because each row in the data view represents one subject. So because we have taken 3 measurements from each subject in this particular example, we're going to have 3 more variables that represent each level of that within subject factor. And because each of those variable columns are going to have the measured cholesterol concentration, that variable is a ratio or scale data. So all of these dependent, or not dependent, all of our within subject levels should be listed as scale. Okay. If you only had 2 levels of your within subject variable, you'd only have 2 rows in this variable view. If you had 6 levels, you'd have 6 rows, right? So that's kind of like how you can cross-check to make sure that your data are organized correctly, is think about you've got one variable set for your between subject independent variable, and then the rest of the variables are going to be based on how many levels of your dependent or not your dependent, how many levels of your within subject factor you have. So once that's all set up, it should end up looking something kind of like that in SPSS. And you can see our data labels are associated with each of our subjects. Okay, so this grouping here are my sedentary people, and then grouping 1 is my low intensity. If we kept scrolling through the data view, we would have labels of 2, which would separate out our high intensity people. But once this is set up, then we can go into the actual setup of the test. So again, we'll assume we have a normal distribution and no significant outliers for our dependent variable. Most of the data sets I end up choosing are usually good, or they've been created through random number generators, which will usually give you a normal distribution. So we don't have to check those, but there's still an assumption that you should acknowledge when you're writing out your assumptions in the activity. For this setup, we're going to take the same pathway we used last week. So because we have a repeated measure or within subject independent variable, we have to use the repeated measures test. So analyze general linear model repeated measures. That'll bring up the dialog box for you to identify what your within subject independent variable is. So in this example, it's time of measurement. And we have 3 levels, pre, mid, and post. So once you define that information, you can click add, and then it'll put it into that box. The measure name is our dependent variable. So that was our cholesterol concentration. We can click add, that'll put it in this box, and then we can click define, which will take us to our actual test setup where we identify other things. So now in our within subject variables box, we've got in parentheses time. Since that was the only within subject variable we identified, we said 3 levels. So whatever number 1, 2, and 3 you want to associate with your within subject levels is like completely up to you. They're noted in the output, so if you forget, you can always go back. But this would represent the pre, the mid, and the post measurement. So we could highlight each of these levels and input them into that area. That would end up looking like that. And then our group or exercise intensities is our between subject factor. So that's what this box is for. You can transfer group into between subject factors. And then from there, we set up our post hocs by going to the estimated marginal means. So once you click on that button, we can then transfer all of our main effects that we're interested in looking at our post hocs for. So we transfer them into the display means for box, set them up with the Bonferroni adjustment, click continue. That'll take you back to the repeated measures dialog box. And then we go to options, make sure we have our descriptive statistics and estimates of effect size. This will generate your partial eta squared values. And the homogeneity test needs to be checked because we've got a between subject independent variable. So whenever you're doing, what was it, two-way, I think this options box pops up for both your two-way independent and your two-way repeated measures. So the only times you're going to check this homogeneity test box is when you have a between subject factor. So that would just be for independent ANOVAs, or it would also be for mixed ANOVAs. So once you have these selected, we'll click continue. That'll take you back again to the dialog box, and then you'll click on the paste button at the bottom of that window, which will bring up our syntax window so that we can set up our pairwise comparisons for the interaction effect. So when this pops up, all you're going to see is that you've got estimated marginal means set up for the group and time. So those are our two independent variables. And then we have to add in the compare group and compare time lines so that we can get our pairwise comparisons for our interaction effect. Once those are inserted, we click on run all, and then we get an output. So questions up to this point? Most of it's the same as last week. So, okay. I don't see any objections, but I'll keep my eye on the chat box just in case. Okay, from there, we set up our test. Now we check our assumptions. Remember that for a mixed ANOVA, we have to check Mauchly's test of sphericity for the within subject factor, and we have to check Levine's test for homogeneity variances for our between subject factor. If you forget to check the homogeneity test box in the test setup, you will not get a Levine's test in your output. So if you're running a mixed ANOVA and you know I have to look at homogeneity variance and it doesn't show up, it's probably because you forgot to check the homogeneity test in the setup. So you can always go back and like redo that. But we're going to check Mauchly's test first. So our between subject factor was, or within subject factor was time. In Mauchly's test, we have our p-value listed. So the null hypothesis for sphericity is that the variances of the differences between the levels of time, or between all of our time points, are relatively equal. Since we have a p-value greater than 0.05, that would indicate that we accept the null hypothesis and we assume sphericity for time. So in this particular instance, sphericity is met. So that would tell us we read sphericity assumed for time in our ANOVA table. You'll notice that in our sphericity test last week in our repeated measures, sphericity for the interaction effect was also included in this table. That is not the case when we have both a within and a between subject factor. So if you accept sphericity for your within subject factor, you're also going to assume that you're going to use the same, or you're going to have the same assumption for the interaction effect. So in this box here, I've said we're going to do sphericity assumed for both time and for the interaction. And then a special note, if your within subject factor only has 2 levels, you assume sphericity anyways. And if it only has 2 levels, you assume sphericity for your within subject variable, then you would do the same for your interaction effect as well. In the case where you violate sphericity, which again, not the case for this example, but just a what if scenario, we then look at our epsilon value in the greenhouse geyser box. Okay, so if we had a p-value in this sig column that was less than 0.05, we'd say, is this value in this box less than or equal to 0.75? If that's the case, we would end up using a greenhouse geyser adjustment for both time and our interaction effect. If that epsilon value in this box was greater than 0.75, then we would use the Hunefeld adjustment for both the within subject variable as well as the interaction. So general rule of thumb, whatever you do for the within subject variable, you treat the interaction effect the same way. Okay. So that assumption's checked off. For this example, we've assumed sphericity. Woohoo. Okay. Then we have to check Levine's test for our between subject factor. So this is where I was saying it kind of gets a little bit intimidating because, or it can be confusing, because when you look at the full table, you're going to have 3 p-values. So we've got 1, 2, and 3. How they are labeled is what is confusing. So homogeneity of variances is looking at if we have equal variances between the levels of our between subject factor. So in the past, we've said there are equal variances. For our case, there are equal variances between exercise intensity programs or exercise programs, right? That interpretation is still going to be the same, where you say equal variances between the levels of our between subject independent variable. However, when you look at the labeling, pre, mid, and post-intervention measurements, these are levels of the within subject variable. So some students get confused because they're like, well, I thought Levine's test was supposed to look at the between subject variable, and it does. What this would be interpreted as then is that we're looking at if the variances between the levels of our between subject independent variable, are those variances equal or not when we look at those levels within each of the levels of our within subject variable. So we would say, what are the variances for our sedentary, low intensity, and high intensity groups when we just look at the pre-intervention measurements? Are the variances equal or are they not? In this case, they are, because p-value is greater than 0.05. And then we would do the same thing for the mid-intervention, and we do the same thing for the post-intervention. So the number of p-values you end up getting in Levine's test is going to be equal to the number of levels of your within subject variable, because you have to check if you have homogeneity of variances within each level of that within subject variable. So to like break this down a little bit more, I've created a separate slide for each of these p-values, so the tables have been cropped. But if we look at the pre-intervention p-value, right, our equal or null hypothesis would say there are equal variances between exercise groups within the pre-intervention measurements. P-value is greater than 0.05, we have equal variances. We've met our homogeneity of variance assumption. If we violated it, same thing that we had for our two-way independent ANOVAs, we don't really have an adjustment factor that we can apply to our degrees of freedom in the repeated measures test or analysis, which is where we got this output from. So if you violate any of, or if any of your p-values violate homogeneity of variance, just you note the violation, just keep moving forward like normal. But that would be for our pre-intervention measurements. Then we'd look at if we have equal variances within our mid-intervention measurements. So null hypothesis, again, are there equal variances, or there are equal variances between our exercise groups within the mid-intervention measurements? We can assume this is true because our p-value is larger than 0.05. And then we would do the same thing for the post-intervention. So based on this p-value, 0.482, that is larger than 0.05. So we have equal variances between exercise groups within our post-intervention measurements. A nice distinct way that you can, if all of your values are larger than 0.05, like we have in this scenario, you could just say equal variances, or there are equal variances between exercise groups for each level of time, or for all of the time points that we collected cholesterol at. Okay, so I think I mentioned this in the activity video, but as long as you write the p-values for each one, so you would report like P for the pre-intervention was 0.855, 0.597 for mid, 0.482 for post. Okay. So as long as you include all of those p-values and your interpretation, if you combine everything in one interpretation, that's fine. Just make sure your p-values are listed. Okay. Questions on assumptions? So the way we check them is the same as our previous weeks. You just have to look at them separately because we have both sphericity and homogeneity of variance. But once we know if we've met sphericity and if we've met homogeneity of variance, which is the case for our example, we then can look at our ANOVA results. So I've split these up this time as we're looking at the main effect of our within subject independent variable first, because we have to go to different tables in our output now. So because time is our within subject variable, we go to the test of within subjects effects ANOVA table. In this table, we'll get our p-value for the main effect of time. We'll also get the p-value for the main effect or for our interaction effect. Okay. We'll come back to the interaction effect. So for now, we're just going to focus on this first one. But since we assume sphericity for time, that's why we've got this p-value highlighted, that sphericity was assumed here. Okay. So if we just focus on like that first part, right, we had a p-value less than 0.001 for time. So this is one of our main effect null hypotheses, which the null would say that time has no significant effect on cholesterol concentration. Specifically, we're saying that time has no significant effect when we're not considering the exercise interventions. So regardless of if somebody was sedentary, low intensity, or high intensity, we would take all of our pre-intervention measurements, all of our mid-intervention measurements, and all of our post-intervention measurements, create a mean of each of those groups, compare those means. This is the p-value we get. Okay. So since p is less than 0.05, we reject this null hypothesis, and then we would end up saying there's at least one significant difference in cholesterol concentration between our different time points, regardless of the exercise intervention someone participated in. Because we have a significant main effect, kind of keep a side note, we need to check post hocs for this in our pairwise comparison section of our output. Then we would check our between subject effect independent variable. So within subject factor, within test of within subject effects table. Between subject factor is going to be in the test of between subjects effects table. Group is how we worded for the exercise intervention, right, or the different intensities. So in this example, we've got a p-value of 0.020. The null hypothesis for the main effect of exercise intensity would say that the level of exercise intensity has no significant effect on cholesterol concentration, regardless of when cholesterol is measured. So in this case, we would take the pre, mid, and post measurements, combine all of those together to create a mean for our sedentary group. We'd take all three measurements, combine them together for our low intensity, and then for our high intensity, compare those three means together, and we get this p-value. Okay. So since that's less than 0.05, we would end up saying that exercise intensity has a significant effect on cholesterol concentration, regardless of when we actually measure the cholesterol. Okay. So again, since we have a significant main effect, we would need to look at the post-hocs or pairwise comparisons for group in our output. Then we look at our interaction effect, which was noted in our within subject effects table. So again, this one's cropped from the table I showed you the first time. But we see our interaction is listed with a p-value of less than 0.001. The null hypothesis for our interaction effect is that there is no significant interaction effect between our two independent variables, exercise intervention and time. Since we have p-value less than 0.05, we reject that null hypothesis and we say there is a significant interaction effect between the exercise intervention and time. Okay. So because we have another significant main effect, we would need to look at both sets of pairwise comparisons for our interaction effect. So that leads us to this list for pairwise comparisons, because again, we only check pairwise comparisons when we have a significant main effect. So we identified that our within subject variable time had a significant effect. Our between subject variable group, or the exercise intervention that we applied, also had a significant effect. And then our interaction had a significant effect. So that would be two different levels of pairwise comparisons. We'll start with our within subject factor pairwise comparisons. So in this instance, we had a control group, our low intensity. JK, I went with exercise intensities first. So this is our between subject pairwise comparisons, probably because this one was listed first in the output. Anyways, if we look at the differences between our exercise intensity levels, the p-values are listed in that sig column, and we can identify one significant p-value or one p-value less than 0.05. So that would indicate we have one significant pair, and that's between our control group and our high intensity exercise program. So the interpretation of that pair would be that there's a significant difference in cholesterol concentration between no exercise and the high intensity exercise program, regardless of when our cholesterol was measured. If you don't include the regardless part, that's okay, as long as I can tell that this pair is different from like when you're looking at your interaction effects, then you're fine. Okay, so significant difference between control and high intensity for cholesterol concentration. That takes care of our pairwise comparisons for one of our main effects. For our second main effect, time, 1 in this instance is the pre-measurement, 2 is the mid, and 3 is post. So when we consult our significant pairs, we can see we've got 3, or all 3 possible pairings are significant. The unhighlighted values are the redundant pairs in the table. So we could say our pre and post, and mid and post pairs are significant. We could also just summarize that and say all time points resulted in significantly different cholesterol concentrations, regardless of the exercise program being performed. Okay. All right. We then check our pairwise comparisons for our interaction effect. First, by looking at, hello, clicker, work, there we go. First, we'd look at the differences between our exercise groups within each time measurement. So hopefully this isn't too small on your guys' end. I'm in presenter view, so the numbers are smaller than I remember them being. But when we look at the pre-intervention section, we can see we don't have any significant pairs. This actually is a good thing, right? Because that means that everybody we collected at the beginning of the test, or whoever we sampled, they all had similar cholesterol concentrations to start. So that kind of helps us isolate the effects of the exercise program that we gave to people. When we look at the mid-intervention set of pairs, so kind of this chunk here, we notice that we have one significant pair. Okay, some of you might be looking at this 0.051. Although it's very close to 0.05, it is still greater than 0.05. So we would say that that is not significant. Okay. I do think there is an example in the activity this week where you'll get a p-value reported as 0.050. That is up to you guys. I've seen it in some resources that say if you get an exact p-value of like 0.050 in your output, you don't argue that it's significant because it could be 0.0501. And it's just a kind of a decimal reporting limitation within the software that you use. So that's more of a subjective call. But in this case, like this is pretty clear, it's still greater than 0.05. So we only have one significant pair in our mid-intervention group. And then if we look in our post-intervention measurements, we have significant differences between the control and high intensity, as well as the low intensity and high intensity. Okay. So we ended up having 3 significant pairs. Okay. And we could summarize this by saying cholesterol concentration was significantly different between the control group and high intensity exercise program at both the mid and post intervention measurements, and between the low and high intensity exercise programs at the post intervention measurement. Okay. So lots of different ways that you can write your interpretations, but as long as you get all of your pairs in there, you're good to go. I know some people like to write these as bullet lists too in their like answer sheet write-up. So if that helps keep you organized, that's fine too. Okay, that takes care of one of our pairwise comparisons for the interaction effect. The last one, we're going to be looking at the differences between our time points within each of our exercise programs. So for the control group, we end up seeing, I'll list my pairs over here. For our control group, the pre and post measurements and the mid and post measurements were significantly different from each other. Why this happened, we don't really know, okay? Because the control group didn't do an exercise intervention. So usually when the control group has significant effects, you kind of want to look into maybe if they were actually a control group. So were they eating the same? Was their diet the same? Maybe some people changed their diet and that influenced how much cholesterol there was in their system. Maybe some people, let's see, I think post cholesterol in from the pre to post measurement actually got bigger, or it increased. Mid to post, it also increased a little bit. So that's where you would want to look into, like, okay, well, why are their measurements increasing? Is that a good thing? Is it a bad thing? Do we need to control more variables in our study? But there was a significant difference, or two significant pairs in our control group. In our low intensity group, they had significant differences between the pre and the post measurement, as well as the mid and post measurement. Okay, so kind of similar to the control group. And then our high intensity exercise program had all pairs significantly different from each other. So they had progress in their cholesterol, or differences in their cholesterol concentration for each time they went in to get measured. So we could write this as post cholesterol measurement was significantly different from the pre and mid measurements for both the control and low intensity groups, right? Because each of the control and low intensity groups had the same pairs that were significant, so I just clumped them together. And cholesterol concentration was significantly different between all time points for individuals in the high intensity program. That would cover that set of pairs, or this chunk in the table here. Okay, so that ends up concluding like the stopping point for the ANOVA. Then the question I usually ask you guys is to report the effect size. So again, two-way ANOVAs, we use our partial eta squared. That's the effect size that's automatically included in the test. When we did our two-way independent ANOVAs, to find the effect size, you guys looked in the main ANOVA table and then associated the effect size of each independent variable. So same thing here. For our between subject independent variable group, or the exercise intensity that we program that we gave people, there's a partial eta squared listed in the table. That would represent the effect size for the main effect of group. Okay, so we would interpret 0.171, right, compared to 0.14. That would be considered a large effect size for the differences between exercise intensities. For the main effect of time, our effect size is listed in the main ANOVA table, or the within subject effects table. And again, you choose the effect size usually is going to be the same for any of the adjustments, but you read the one that correlates to the adjustment you ended up using. So since we assume sphericity, that's why I highlighted the partial eta squared value in that top row. But we have 0.903, that's greater than 0.14, which indicates we have a large effect size for the differences between time points. This test of within subject effects also has our interaction effect. I have had like a small handful of people from both sections who were reporting the effect sizes that were associated in this within subject effects table for the interaction effect. Remember that you can pull the effect sizes from these main ANOVA tables for each of the independent variables, but for the interaction effect, you have to consult either the multivariate or univariate tables that are underneath the pairwise comparisons. And unfortunately, in mixed ANOVAs, you're going to get both a univariate as well as a multivariate table. It kind of just depends on which comparison you're looking at first. So this univariate table, Juan said, oops. Cool. Maybe that's like a nice thing to note going back to activity 8 before you submit it tonight. So in this univariate table, I pulled this out from, it was underneath the pairwise comparisons table that was looking at the differences between our exercise programs within each of the time points. Okay, so each of these effect sizes is representing the differences between exercise groups within the pre, the mid, and the post measurements. So clicker, there we go. For the pre-intervention, this would be considered a small effect size because it's kind of close to 0.01. So that would be our respective interpretation. I put an asterisk next to the mid and the post interventions because usually I ask you guys only to report the effect size or effect sizes for the significant interaction pairs. So if we had gone back to our pairwise comparisons, we had significant differences in the mid and the post groups specifically, or between those two time points. So in an activity, you would only report the effect sizes for the mid intervention and for the post intervention measurements. Both of those would be considered large effect sizes for the differences between exercise intensities at their respective time points that cholesterol is measured. Okay. And then the last set, hold on a second, chat. This was for the table that pre being 1 for all columns. Pre being 1. I'm not really sure what you're referring to on. So let me go back. This univariate table was underneath this set of pairwise comparisons. Yeah. Okay. Cool. All right. Our last set of pairwise comparisons is going to be for the second set. So, or too many words in this class. I can't. These are our effect sizes. This effect size table was reported underneath the pairwise comparisons table here. So these pairwise comparisons were looking at differences between time points within each exercise intervention. So the effect sizes that are reported in this table are telling us the size of the difference, or the size of the mean differences between time points within each intervention group. Okay. So we had significant pairs in each of our intervention groups. So I put an asterisk next to all of these. Again, you could list your interpretations separately. They're all large effect sizes. Or you could kind of combine them into one statement, saying like there were large effect sizes for the differences between time points in the control group, and then you would list the effect size for the control group. In the low intensity, list the effect size, and for the high intensity exercise programs. Okay. All right. Questions on any of this? Or do you want me to repeat anything, go back? Okay. The process, the nice thing about this is the last 3 weeks, you've been doing the exact same process every single time. So that in and of itself should be helpful because repetition is good for solidifying concepts. In case any of you are interested in looking at it, I can show you what the output looks like, or at least the organization of it. You'll see the same thing in the activity video, but and I've cut out things that we don't need in here. But we have a list of our within and between subject factors, so that tells you what each label means in your output. Mauchly's test of sphericity will show up first. And then we end up seeing our test of within subjects effects. So in this one, I don't know why it didn't save my highlight. In this table, we've got both the within subject independent variable p-value as well as the interaction effect p-value. And then we also have the effect size for our within subject variable. Underneath that, you then get Levine's test for homogeneity of variance. And then underneath that, you get your test of between subjects effects ANOVA table. So that would tell us the p-value, which was 0.020. Oh, I remember because I was making separate examples for the PowerPoint. That makes sense. So we have p-value as well as the effect size for group. And then past that, we get our estimated marginal means, our pairwise comparison section. So pairwise comparisons for intervention group. We get pairwise comparisons for time. And then our two interactions. So pairwise comparisons for differences between our exercise programs within each time point. And then you can see the univariate test is right underneath that. So that way you can cross-check, all right, I had significant pairs in the mid-intervention and post-intervention groups, therefore I'm going to report these last two effect sizes. Okay. Same thing goes for the last set of pairwise comparisons for the interaction, where we looked at differences between time points within each exercise program. And since each of these groups had significant pairs, we would end up reporting the effect sizes for each of those exercise groups. Okay. All right. I think that's probably enough for today. Do you guys have any questions before you take off? Okay. I'm gonna stop recording.